So last time we had class, we talked about three specific trends on the periodic table. So you notice that we have our periodic table here, and we're going to talk about the three major trends and how they actually work together in terms of the periodic table. So on the periodic table, we know that there are specific things that happen. One of the ones that we talked about was this idea of ionization energy. Keep in mind that ionization energy is the energy required to pull an electron away from an atom or an element. So ionization increases as you go up and to the right, which means that things like helium over here have the highest ionization energy possible. It's really difficult to pull electrons away from those. The next idea that we talked about is an idea that we call electronegativity. So electronegativity is the attractiveness of an element, or how likely it is to actually pull electrons into that atom. So the higher the electronegativity, the more likely it is to kind of pull in these electrons that are in the environment around them. Electronegativity actually follows the exact same trend that ionization energy does. So as you go up and to the right, electronegativity also increases, which means things like fluorine over here has the highest electronegativity possible. It really, really likes electrons. But things down here, like francium, have a really low electronegativity. They don't like electrons that much. They're not very likely to pick up any more. The third trend that we talked about is actually this idea of atomic radius. So remember, atomic radius is the distance between the nucleus of the atom all the way out to the edge of the electron cloud. Atomic radius actually works the opposite way. So atomic radii increase as you go to the left and downwards, meaning that things like francium have the largest atomic radius, and things like helium over here have the smallest atomic radius possible. So again, all of these arrows indicate increases. So the increase for atomic radius increases as you go to the left and down. For electronegativity, it increases as you go up and to the right, and for ionization energy, it also increases as you go up and to the right. All arrows on our diagram right now are about increases. So now there's a specific tie-in between the atomic radius and things like ionization energy. So in here we have a really small atomic radius because those electrons are really, really close to our nucleus. Now because they're so close, this positive charge in our nucleus, these protons, have a really strong attraction between these and our electrons. So it's a really strong pull. Because this pull is so strong, it's really difficult to pull electrons away. So remember, because again they're really close, we have this really strong pull, it's really, really difficult to get electrons to free themselves away from our atom. So it's really difficult to pull them away. Because it's so difficult, we actually get a really high ionization. So because this pull is so strong, small atomic radius actually means high ionization energy. So high ionization, because it's really, really difficult to free these electrons away from their orbits. It's really difficult to get them away from it. On the flip side, when we have a really large atomic radius, that pull isn't as strong because they're really far away. Now because that pull isn't so strong, it's actually really, really easy to pull these electrons away. So a large atomic radius actually means a low ionization energy. It's really, really easy to pull these electrons away. So those two trends actually go along really well on the periodic table. The bigger the atomic radius, the easier it is to remove electrons. The smaller it is, the more difficult it becomes. Our last and final piece actually has to do with the idea of electronegativity. What does it mean? Why does it work the way it does? So we've talked about noble gases, and we've actually talked about there are some of the most stable things that we have on the periodic table. It's why we use the noble gas electron configurations. So if we deal with something like argon, we know that it's really, really stable. However, if we use the noble gas configuration, things like potassium have this argon built into them, and then they have some additional orbitals they need to fill. So argon plus 4s1 is really potassium. Now, all of our elements on the periodic table really want to look like the noble gases. So in terms of our electron configuration, the way that potassium can make itself look like argon if it gets rid of this extra electron. Now, if it gets rid of this extra electron, remember that it picks up a positive charge. So potassium plus 1 is actually the same thing, electronically speaking, as argon. So now it's electronically stable, it's very content. But because it really doesn't like this electron, we can say that it has a really low electronegativity. It gets rid of this electron, and now it's happy. So things like potassium, or things over on the far left that have a low electronegativity, they have a low electronegativity because they're already so close to being that noble gas. On the other side, if you're looking at something like fluorine, so something like fluorine, in order for it to get to that next noble gas, if we're using our noble gas electron configuration, it looks a lot like this. In order for fluorine to get to the next noble gas, we actually have to input an electron, which means it ends up looking like neon. But this is why fluorine has a really high electronegativity. All it needs is one more to look like the next noble gas. It's all about how do we get there in the easiest way possible. For potassium, the easiest way possible is to kick out this electron. For things like fluorine, though, the easiest way to get to the next noble gas is to gain one more electron and turn negatively charged. The goal is always to get to that noble gas. How do we get there, and by what means can we make this happen?